We started talking about rates of change, or recapping rates of change, the other day, and one of the classic rates of change questions, and we looked at this a little bit when we were looking at exponentials, if I remember, didn't we? Growth and decay, didn't we? Basically using the idea that growth and decay is always proportional to the population. So we know that the rate of change of population will be some constant times what the population is. So it's a very simplistic model. The solution to that is P equals AE to the KT. So P represents the population at any particular time. A would end up being the initial population. If T was equal to 0, we'll get e to the power of 0, which is of course 1. So A. K will be our growth, or if it was negative, decay, constant. And T represents time. There's P. Differentiate it, we get Ka e to the KT. But AE to the KT is P. So there we go. The P to T is equal to some constant times the population. Okay, so let's have a look at this example. We've been told that the growth rate of bacteria, 10% of the population. So crawling all over you at the moment is all this bacteria. You can't see it, of course, but trust me, it's there. So just imagine all these things crawling all over you. But it's all right. Initially, there's only 1 million of the things on you. So you have 1 million of those. Just like that caterpillar the other day. They're a lot smaller, So you got 1 million of them on you. Okay. Standard sort of question is, like I just did, well, let's prove that, or show that this is a solution to the differential equation. It's all right, P is AE to the, well, in this case, I know what K is. They've told me that it's 10% or 0.1. We'll differentiate it, and there we go. We get 0.1 times P, so we get K times P. So it does solve our differential equation. So after 3.5 hours, those 1 million little gooby wops crawling all over you at the moment, in 3.5 hours' time, how many will now be crawling all over you, just to make you feel a little bit more comfortable there? Well, we've got to work out a few things here. First of all, we'll work out A. Well, A is the initial population. Now, whether you just look at it and go, oh, initial population is a million, or formally substitute in T equals 0 and prove A is 1 million, we get our P now, instead of AE to the 0.1 T, we have 1 million E to the 0.1 T. And we want when T is 3.5. So sub in 3.5, and we almost have another 500,000 of them. Gosh, that's just in 3.5 hours. Now you can see why it's important to take a shower every day. So after 3.5 hours, there's 1,419,000 little gooey ops crawling all over you. Let's have a look at a decay question, one that goes the other way. So there's this isolated island, and in 1960 the population was known to be 1,732, but clearly these people did not get on with each other, because in 1970 the population was 1,260. So they're either killing each other or, well, I don't know what to do with them, but they clearly don't like each other. Find the annual growth rate, which in fact will end up being a decay rate, assuming that it is proportional to population. So if we assume it satisfies our simplistic model, the P to T is equal to some constant times the population, it is okay to just jump to the solution. We know the solution to this is P equals AE to the KT. We've just got to work out what A is and K is. Well, K is the actual growth rate we're trying to find. So initial population 1,732. So we can change our equation to P equals 1,732 E to the KT. We know 10 years later the population is 1,260. So E to the 10K is 1260 over 1732. Undo the exponential, we do the inverse function. Inverse to exponentials is, of course, logs. So 10K is log of that particular fraction. K will be 1/10 the log. So there's the exact value. They've set to the nearest percent. So we bung that in the calculator and we get negative 0.0318165 So roughly 3%, decaying at 3%. So how long is it going to take for the population to halve? 866 is 1,732, because 866, of course, being half of 1,732. So we're now solving e to the kt is a half. I left it as k rather than writing, what was it, the log of all that. Store that in the memory of the calculator, use that, rather than use the approximation, because with something like an exponential, which grows, rises pretty quickly, you could get a rounding error if you use the approximation. So I'd be storing that exact value of k in the memory of your calculator for this. So t is 1 on k log a half, which actually happens to be the formula for half-life. Where do you do that? Physics? Chemistry? Yeah, so I mean that's where the formula basically comes from. 21.786. So this is always an interesting question. In how many years will the population be half? Well, I'm going to say in 22 years. That's kind of easy because it said 21.7. If it said 21.2, I'd probably still say 22 years. Because at 21 years, it hasn't halved yet. So, but to make sure of everything, I'd be saying, make sure you write down your decimal answer for that so they can say, yes, you got the calculation right. And if you're rounding up when it looks like you normally round down, maybe you'd explain that as well in your answer so they can see, no, I'm not an idiot. I do know how to round. This is why I chose 22. Oh, that's just, well, not many questions at all there, is there? 16b.